Greetings and welcome, friends. Big day. It's a big day for functions. This is amazing. We are talking about function notation, which notation, just think about like how you write something. How you write something, okay? So we're not changing what we're talking about. We're just changing the way we write it is really what it is. And function notation, this is something that's going to carry through with you really straight through like calculus 4 at least if you go to college and take up to calculus 4. Function notation, I've got to remember, was that Descartes? I don't remember who came up with function notation, but either way, you could YouTube it, you could Google it, you could Wikipedia it, and you will know who came up with function notation. But nonetheless, it's something that has affected mathematicians for generations. It's going to continue to be a way that we communicate about functions. It says this, okay, all right, presumption there, I understand. Maybe you don't know, but let's pretend we do. You know that a linear function can be written of the form y equals mx plus b. By naming a linear function f, you can also write the function using function notation. I'm not changing what it is, I'm just changing the way I represent it. In function notation, I would read this as f of x. So that's how you would read that. F of x equals mx plus b. All right, f of x, or the function f, when I plug in x, is equal to the following. All right, so that does not mean f times x. Notice that it's a cursive f, so I'm talking about this equation. It's the name of the function. You can also use g of x or h of x, different things like that. And so the notation f of x is just another name for y, okay? Notice that f of x and y have replaced each other in position, like so. So here, previously we talked about y as the output of a function. F of x is also describing the output of the function. The output of the function is equal to this, right? It's what I get after I do all of the things that the function told me to do to x, to the input. So this is equal to the output, all right? This is equal to, it's the same as y. It's just another way of writing something. Good, good. So let's see. So if f is a function and x is its domain, then f of x represents the output of f corresponding to the input x. All right, we'll figure this out. Don't you fret. Don't you fret. Okay. And then, yeah, you can have other names for functions as well, which sometimes shows up. There's more than one function you might be talking about at a given time. All right, so here we go. If I've got f of x equals negative 4x plus 7, I want to evaluate when x equals 2. So the way I do this, watch this, I'm going to write f of negative 2, which is asking the question, what does this function equal when x, notice the inside of this, x is negative 2. If I plug in negative 2, what is the output? And so f of negative 2 would equal negative 4 times negative 2 plus 7, which is equal to, now I just order of operations this, I'm just PEMDASing it, PEMDAZZLE, excellent. Negative 4 times negative 2 is positive 8, plus 7, and I get 15. So make sure you're writing this down on your little examples there. So f of negative 2 equals 15. All right. Guys, what did I do? I did negative 2 already. I was supposed to do positive 2. All right. Yeah, silly me. That's all right. I'll just claim that I did this side first. All right. So notice I took the fact that x is equal to negative 2 and I replaced the x spots with the negative 2. All right. So now I'll do this one. Oh, silly Mr. Waddy, huh? Doing it a little bit backwards today. That's okay. So if I want to figure out what is f of 2, that means what is the function equal to when I plug in 2 for x. So that would be negative 4 times 2 plus 7, and I get equals, negative 4 times 2 is negative 8, plus 7. Negative 8 plus 7, their signs are different. I think you would agree. And so I will get 8 minus 7 is 1, and 8 was the more influential, so it's minus 1. F of 2 equals negative 1. So this is the same as if I represented this as an input-output table. I could have done x and y. I also could have described this as x and f of x, all right, as my input-output. And I would have had the following, right? I would have had negative 2 and 15. I would have had 2 and negative 1. These are also the same if I was to represent them as an ordered pair. This is the same as negative 2 comma 15. This is the same as 2 comma 1, sorry, negative 1, all right? So that's different ways of representing the same information. We've also could represent those points graphically, where from the origin I would have gone left 2 and up 15, or here I would have gone right 2 and down 1 to plot the point graphically. Let's see, I think I gave you these examples as well, just because I really want to make sure we get this idea of function notation. All right, let's see. Here we go. Function notation. All right, did I give you guys these examples? Awesome. All right, so if I want to figure out what is the function equal to when x is equal to negative 4, I would write f of negative 4 equals 2 times negative 4 minus 5. 2 times negative 4 is negative 8. Minus 5 equals negative 13. So f of negative 4 equals negative 13. So this is communicating to me that when I plugged in negative 4 for my function, I got negative 13 as the output. All right, so let's see, f of 0. Ooh, F-Zero, classic Super Nintendo game that had like all the, was it parallax? What was the thing when they took 2D graphics and tried to angle it and make it look 3D? Oh, it was classic. Such a classic game. Let's see, 2 times 0 means f of 0 means I'm replacing x with 0, right? The input is 0. So 2 times 0 is 0. 0 minus 5 is negative 5. So I get f of 0 is equal to negativo 5. And let's do one last one. Let's do f of 3. Right? So that just means you're plugging 3 in as the input. F of 3 represents the output. Okay, so 3 is the input, f of 3 is the output, and the output is found by evaluating the function when I plug in the input. All right, it's weird getting used to writing it this way, but I assure you, you'll do fine. Let's see, 6 minus 5 is 1. So f of 3 is equal to 1. So if I wanted to think about that as an ordered pair, that is the same as 3 comma 1. My output is 1. The y is 1. Good? All right, let's do this last one pretty quick for this evaluating functions. So let's see. So g of negative 4 would equal the opposite of negative 4 minus 1. Careful with these double negatives here. Opposite of a negative is positive. 4 minus 1 is 3. All right, picking up the pace. All right. If you already wrote the other example, you could just follow along and listen to this last one. Just try to absorb the idea. G of 0 means I'm plugging in 0 for x. And so the opposite of 0 is negative 0, which is still 0. 0 minus 1 is negative 1. So G of 0, when I plug in 0, I get negative 1. The output of function G, hey, I didn't even realize, we're using another name. This is great. I love it. And let's figure out what G of 3 is. G of 3 is equal to the opposite of 3 minus 1. Negative 3 minus 1 is negative 4. G of 3 is equal to negative 4. Okay? So it's just another way of writing it. Okay? Just another way of writing it. So f of something is referring to the output, just like y did. All right, this is where this gets a little bit interesting. So what we're going to do is figure out what would this mean in terms of this context. What would this mean in terms of this context? So it says let f of t be the outside temperature, degrees Fahrenheit, and t hours after 6 a.m. So where's my cursor here? So this is my input, all right, and the output, all right, is the temperature. Okay, so the output is the temperature, the input is the time measured in hours after 6 a.m. So right here, if time equals 0, what does that mean in terms of hours after 6 a.m.? What time of day is it? It's 6 a.m., all right? T equals 0 corresponds to 6 a.m., all right? Does that make sense? So what does this represent? That means, let's see, the output is 58, which is measuring degrees Fahrenheit. So that means it's 58 degrees at 6 a.m. is what that means. All right, the initial value of the function is 58, so the temperature at 6 a.m. is 58 degrees. Okay, all right, okay, this one's trickier. What if the input is 6, what does that mean in terms of time? If t equals 6, what time is it? Well, if t measures hours after 6 a.m., what is 6 hours after 6 a.m.? Yeah, right? That's noon, that's 12, right? That's what this represents. So at noon, high noon, it says the output here is n. So I don't actually know. All I know is that at noon, it is n degrees. That's all that this represents. Okay? All right, this next one's a little bit trickier. Let's see, if when t is 3, what time is it? And when t is 9, what time is it? Okay, what's 3 hours after 6 a.m.? That's 9 a.m. And what is 9 hours after 6 a.m.? This one's trickier. Well, 6 hours after, sorry, I think I said that wrong. What is 9 hours after 6 a.m.? 6 hours after was noon. 9 is 3 more hours after noon. So that must be 3 p.m., right? 3 p.m., 3 in the afternoon. And here, there's a relationship, okay? So this is the temp at 3. This is the temp, sorry, man, this is what's so tricky about this. This is the temp at 9 a.m., and I'm not writing this very well. And this is the temp at 3 p.m. That's so crazy because the 3 represents 9 and the 9 represents 3. Not the most helpful. And they're saying that this one is less than the other. Okay, I don't even know what those temperatures are yet. Okay, all I know is that it is colder at 9 a.m. than 3 p.m. Okay, does that make sense? The output of the function, the temperature at this time, is less than the temperature at this time. Right? It's kind of weird, but just to kind of like get used to like what do these things mean. It just takes a little bit of while getting used to there. All right, let's do an otro example here. Okay, solving for the independent variable. Example trace is for h of x equals 2/3 x minus 5. Find the value of x for which the output, remember that's what this represents, when is the output equal to -7? Okay, so I'm searching for x, and I want the output to equal -7. So if the output is equal to -7, then I'm going to replace the entire output with -7. So -7 equals 2/3 x minus 5. And now I'm going to solve for x, right? What is the value of the input when the output is -7? I've replaced the output. Now I'm going to solve for the input. A little bit weird, but you just set it up, and now we solve. So x is being multiplied by a fraction. It's being subtracted by 5. The inverse operation will be addition first. So let's see, add 5 to both sides. And I'll get -7 plus 5. Signs are different. Subtract them. I get 2. Who is more influential? Oh, this 7, right? 7 is further from 0, so I'm going to keep the sign of the 7. Equals 2/3 x. These guys canceled out, so that makes sense. I'm going to leave that blank. And let's see, we just talked about this earlier. How do I get rid of this? I multiply by the what? The reciprocal. Multiply by the reciprocal. Multiply by 3/2. So behold what happens here. I get x by itself. One move, bam, destroyed that fraction. And over here, hey, actually I can cancel out this 2 with this 2, and I'll have 3 times negative is -3. I'm going to write this in 2 steps, is equal to x, or x equals -3. Okay? So x equals -3 when h of x equals -7. Okay? Or I could have written that as h of -3 equals -7. Question? Or are you just stretching? All right, enjoy a good stretch. Actually, everyone could have a nice stretch right now if you guys want. You don't have to. It's up to you. You could stretch. Nah, you don't have to. All right, let's here we go. Let's giraffe a problem. Which, to be honest, it's my honest review. Giraffing is not my favorite thing to do. Graphing, oof, it's quite a bit of work. It makes it a little bit easier being able to at least have some nice coordinate planes already drawn up for us. Here we go. So, and we're going to actually have better and better means to graph as we go on through this course. Let's see. Step 1, we're going to make an input-output table. So I'm going to have x, and I'm going to have f of x. Okay? If you want, you could make a work column, but you don't have to. When graphing things, in general, I want you to have like 5 points to work off of. In this case, do you guys think this is a line? Well, they told us it's a linear function, so yes. Also, it's of the form mx plus b, so yes. If it's a line, I might let you get away with just 3 points. All right, because then you'll just connect the dots and draw the line. The book, they're doing 5 points right here. We'll just do 3. So a good 3 points to pick. It's not a bad idea to think of what happens when I have a negative, what happens at 0, and what happens for a positive. And we might as well just pick some small nombres to work with. For sake of time, we're going to evaluate these real quick. What is f of -1? I'm just going to do this in my head. Ready? Follow along. 2 times -1 is -2. -2 plus 5 is 3. All right? All right. Plug in 0. 2 times 0 is 0. 0 plus 5 is 5. And 2 times 1 is 2. 2 plus 5 is 7. Okay, so now if I want to graph this, my x values, I got some negatives, I got some positives. Let me select my line tool here. I'm going to just draw a nice little coordinate plane. Oh dear. All right, so this will be my y-axis. Here, I'll make it a little. little thicker there. All right, there's my y-axis. Because I divided these sides evenly because I happen to pick a negative, a positive, and 0. That's why I did that. For my outputs, so far my domain is 3, 5, and 7. So when I figure out how I'm gonna zero in on this graph, so far all of my numbers are positive. Okay, so I'm not gonna make my x-axis in the middle of the graph. I'm gonna just kind of make it here, just so that it shows up okay. All right, so if I plot these points, -1, 3, starting from the origin, that's left 1, up 3. Oh, did I not give myself enough space? Guys, I don't think I gave myself enough space. Oh, embarrass me. Color me embarrassed, maybe. Erg. All right, let's give myself one more here. All right, there we go. We're good now. So let's see. -1 up 3 is right there. Then I'll have 0, 5. So don't move left or right from the origin. And go up 5. I would have been able to fit the other one, I guess, but just fits a little nicer here. And then 1, 7 would be starting at the origin, go right 1 and up 7. And now we will draw our line by connecting the dots. Look at this. I'll just line it up, line up my line and draw these dots. Let's see, something like that. Okay? And so here's a linear function that we graph using table of values. Eventually, we will have better strategies to graph, but right now, table of values is what you got. Table of vowels. Let's see, let's do the last example, the one with a helicopter. Example 5. All right. Ooh, guys, action problem. Here we go. We got a helicopter. My younger brother, Carl, with a K, was at one point a helicopter tour guide, or actually a glacier tour guide in Alaska, and they would take a helicopter out to the glacier. Seemed like a pretty cool thing for someone to be able to do. I don't know. Let's see. So here we go. This problem, I'm dedicating it to my brother. You guys can let him know. Carl with a K. Good times. Actually, since you guys know my last name and now his first name, you could actually narrow him down because there's only one person in the world with that name. So, well, with the last name Waddy, it's pretty rare. There's only a handful of us. Well, actually, that would be some sort of mutant hand with probably about 200 or 300 of us. I don't know. But anyways, let's see. The graph shows the number of miles a helicopter is from its destination. The miles from its destination after an input of X hours on its first flight. So X hours of flying, how far is it from its destination? On a second flight, okay, the helicopter travels 50 miles farther and increases its speed by 25 miles per hour. The function f of x equals 350 minus 125x represents the second flight, where f of x is, once again, that's an output now. The number of miles the helicopter is from its destination after an input of X hours. Which flight takes less time? Okay, so this is the first flight's graph, distance in miles from the destination over time measured in hours. Hours. We'll call it hours. So let's see. So I got to graph this second function. All right, is what I would do. Would be an interesting thing. So I'm given a function in a graph. It asks which flight takes less time. So what am I asking there? I'm actually asking when is when the distance is 0, which one has the smaller so let's see, when the output is 0, which one had the smaller time? okay? So if I wanted to call this graph, which they should have, give it a different name, that's what I'm asking. Which one will the other flight land here or there or there? Which one is faster, okay? Let's make a table of values for our second function. So I'll have x and f of x. Maybe I'll make a work column this time. And okay, so if I input 0 for x, f of 0, I'm going to have 350 minus 0, which is 350, okay? If I input 1, let's see, I'd have 350 minus 125 times 1. 350 minus 125 is 225 miles to go. If I plug in 2, I'd have 350 minus 125 times 2. 125 times 2 is 250. 350 minus 250 is 100. Okay? Let's see, if I plug in 3, I'd have 350 minus 125 times 3. So let's see, that's going to be 250, 375. 350 minus 375 is negative 25. That's weird. I can't be negative 25 miles from my destination. That means I flew right past it. What? It's crazy. Crazy. All right, so let's plot these points. I'll use my classic purple. 0, 350 is right here. Agreed? Yeah. 1 and 225 is right here. Ooh, we're catching up. 2 and 100, over 2, up 100. Oh, we're tied. Oh my goodness, guys, this second flight, it's a comeback. Can you believe it, friends? Wow, he's coming around the bank. He's flying towards his destination. His miles are getting less. He's a 25 miles per hour faster helicopter. Oh my goodness. I cannot believe it. What an upset. 3, negative 25. So I'd go over 3 and then down 25. I draw this line. What? No, you didn't. The second flight, guys, took less time. Can you believe it? I can believe it. Slightly less time. Wow, which flight takes less time? The second flight. And explain because its output at 0 has an input that is less than the other flight. All right, that's kind of the idea. All right, from the graph of the first flight, we see that when f of x equals 0, x equals 3. From the second graph, we see that when f of x equals 0, x is slightly less than 3. Wow, craziness. We could actually solve that, which we've got 3 minutes. Let's actually solve that. Let f of x equal 0. So I'm going to have 0 equals 350 minus 125x. And if I solve this, I would have subtracted 350 from both sides. Right? 0 minus 350 is negative 350 equals negative 125x. How do I get x by itself? It's being multiplied there. What do you guys think? Divide by negative 125, right? And I will get x equals 2.8, which means it takes 2.8 hours for the second flight to be 0 miles from its destination. Good times. Get to work on time, Carl with a K. Yeah, you heard me. You go tour that glacier. Have a good day, internet friends.